Hello everyone. In this session I want to talk about core concepts of mobile development. Some of them are related to Codename 1 and I'll go into that, but most of them are very generic. And the reason for that is that sometimes I see developers coming into Codename 1 and into the mobile world and suddenly hit with realization that, oh, you can't do that in mobile, or you can't do that in a cross-platform way, or this is only applicable to Android and lots of other things of that nature because they're not familiar enough with the restrictions and limitations and the mentality that exists within this particular niche. And here I'd like to talk about some of these things. I don't know if everything will sink in, but to sort of give a sense of why mobile is so different from desktop programming or server programming, if those were the experiences you had before, and also if you just started out in mobile, it gives you a better sense of where the limitations are. So the first thing I want to talk about is density, because density and device resolution are, well, most of us know about them to some degree or another, but even people who know what density is, I sometimes run into the unintuitive nature of this particular problem. So first, density is the dots per inch, or the points per inch, or the pixels per inch. It's essentially how close the pixels are to one another. So if you take an inch, for instance, from an iPhone 7, and you look at it, you can count literally 401 pixels if you'll have a big magnifying glass or something. And you'll literally be able to count lots of pixels there because it has a relatively high pixel ratio, although nowhere near some of the Android devices which go above 600 and even more. Older devices and even relatively new devices sometimes are as low as 100 ppi. And that initially it doesn't seem like a big deal. Most of us are obviously usually focused on resolution. But here I give a relatively simple example of two relatively new devices, iPhone 7 Plus and the iPad 4. Both of them are relatively new. The iPad 4 is almost twice the size of the iPhone 7, but they have almost the same number of pixels within them. And there is a difference. There's a few hundred pixels difference, obviously, but it's not as much as you'd expect there to be. And the reason is the iPhone is far more dense than the iPad. And the thing is that when you take a device that's a tablet and you take a device that's a phone, usually people expect the tablet to have far more pixels, and that's not always true. Now, I didn't find a good graphic to represent density, but I did find a great graphic from OpenSignal that you can see here that represents the number of resolutions that we have for common Android devices. This is only Android devices. iPhone devices are much simpler, but still, the variety is astounding. And you really need to be resolution independent when you're working in mobile. And unlike web designs where you can say, okay, I'll design to a specific resolution and people will just have lots of white space. In a phone, people won't accept that. They want the UI to fit. So a lot of the cheats that we had on the web, we can't do them here. We need to actually use the available space. So lots of the differences, as I said, can be very extreme. If you take a relatively low resolution image and try to show it on a very high density device, it will look very pixelated, and that's something you just can't fix. So you need high resolution images. The problem is that usually low DPI devices have less memory, because usually when we want to build a device, we don't want to stick in too much memory, because that brings up the price, that brings up battery usage, that causes a lot of a cascading sort of effect. So these devices usually have less memory, so they will really be hit if we have too many high resolution images. And also, scaling down a high resolution image doesn't look as good. It doesn't look as bad as scaling up, but you still get artifacts that are not as bad, but still artifacts. And that's not an option either. So there's two solutions essentially for the density problem. The first solution is the one that we use most often, because it's essentially the easiest. All operating systems have a solution of this type, all mobile operating systems that have a solution of this type, and that's to include images for the various DPIs. And the way that it works is you give an image for a high resolution DPI, for high density DPI, and lower and lower and lower, and each one is adapted in smaller. And that way, in runtime, you request an image and you get the right resolution image. In Codename 1, we have that, we call it multi-images, and we do it sort of seamlessly. You just give us a high resolution image and we scale it. Now, on the device scaling, we'll have artifacts, but when we do it on the desktop, we can run a very refined algorithm that scales things with a very high quality. And you can't really do that in runtime on a device. It will be too expensive. But on the desktop we can, and that way when you get a multi-image, you can literally get very accurate, accurately sized image. And that's probably the simplest approach, and the one we usually take, because we get resources that are images, and it's really easy to work with that. There is another approach, and that's vector images, vector graphics. And those contain two big genres within. The first, which we support relatively well, is icon fonts. And that allows you to essentially, if you think about it, a lot of the icons are just a drawing that's very similar to text, but just with a specific shape. So there's this trend that's been going on for several years of creating a font file that contains within it various shapes, logos of social network companies, the share icon, and all sorts of, pretty much any icon you can imagine. And there's lots of great repositories that contain many icon types like that. And we have built in the material design icon set from Google, which is free for any sort of use. And that's why we bundled it in, so we can use it within our code to represent things and have them appear beautifully with icons and everything by default. And that way it's actually pretty small. One of the nice things about icon fonts is that they are, the file, the entire material design icon font is 100 Ks, and it contains quite a lot of icons. And that's pretty cool. We can offer a relatively large amount of icons for literally no cost at all, and just use the drawstring logic to draw it. And it looks beautiful, and it's anti-aliased, and it's just perfect. You can color it based on the system colors, which is one of the best aspects of icon fonts, because if we style a button and we say we want the foreground to be in this color when it's unselected and that color when it's pressed, and the icon font will automatically change the color based on that state. And that's really, really, really convenient. So I love this approach, and we use it a lot. The second approach is vector files. Now, we don't support it at this time because it's not as popular, or wasn't as popular over the years, This started getting some traction in recent years as Google added some support for SVG files into their IDE. Now, no mobile device supports SVG natively. They support it within the web browser, but not for actual drawing. So if you can open a PNG file, you can open a JPEG file when drawing in the native code, but an SVG file won't work. And the reason for that is that it's kind of hard to render an SVG file properly because it contains a lot of information and is kind of bound into the DOM structure of a web browser. And when you start looking into all of the complexities of the standard, your head explodes and you say, okay, let's just leave it for the web browser. So one of the things that Google did, which was something very smart and we wanted to do it too, is an ability to import an SVG file and convert it into Java source, essentially, that you can compile as part of your application, and then it draws everything. And that's something that we have an issue on that, and maybe by the time you view this in a future iteration, it might already be implemented. But it's something that we don't have at this particular time. There is a disadvantage sometimes in the performance of vector files, because when we have an image file, it's just pixels, and the device draws it really, really quickly. It just copies pixels from one place to another, and everything is already rendered. A vector file or a future vector file of this type would be harder to draw at the same performance level. The benefit is that it's obviously smaller and it's very sharp for every resolution. So it's something that we are still interested because the price might be good for some use cases. The next thing I want to talk about is certificates and provisioning. One of the harder concepts in Codename 1 and in mobile development in general. And it will be discussed more in the development process of the bootcamp, but I want to go into details about this in big brushstrokes, because there's a lot to discuss here, even without going into every single detail or into the process itself of making them. So to understand, all mobile OSs require some form of signing by default. There are sort of exceptions, but not really in production. Basically, to actually sell something to a store, pass it onwards or debug it or anything, you need to sign code to run on the device. And Apple and Google and Microsoft have very different approaches to what signing is, why is it there. So Google and Microsoft look at signing as a way to protect your app after it's been installed on a device. So for instance, say you wrote an app and you upload it to Google Play, and you have a Google Play account, you paid for it, it's yours, and tomorrow someone hacks your Google Play account and he's in some foreign country, you don't know who he is, but he now controls your Google Play account. So great, you can report him to Google. But what if during that time he uploaded fake versions of your apps and essentially distributed them to all your users through the automatic update, and now all your users have their data wiped? Well, Google isn't so much concerned about us as developers as much as it is concerned about all of our users, and they don't want that. So what they did here is that they did a double solution here. So if someone hacks your account, that's he broke stage 1. But to upload an app, he'll need your certificate. And your certificate essentially is meaningless. It doesn't say for real who you are. It just says that, yeah, I'm the same guy that uploaded the application initially. So I can create my own certificate. And I'm just saying, hey, I can call myself Bob. It doesn't matter. But the thing is that once I upload an app to the store with the Bob certificate, from this point on, only the Bob certificate can provide an update for that app. Otherwise, that app will not update. So if you lose your Google certificate, it's gone. The app can't be updated anymore. And this is sometimes, it makes things complicated because, you know, sometimes if you build a debug version and install it on your phone, then a release version won't work because they have different certificates. So that's with the Android version. So it's kind of pain, but it's a very convenient approach because you don't need to go to Google and ask them for a certificate. Apple took a very different approach. So with Apple, they're giving you a certificate to indicate that you paid them to build an app. And the logic here isn't just greed, it's also a verification process. That way, the moment you pay them money, they can verify who you are to some degree. And in that sense, they want to weed out the potential that you're a malicious player. At least not of a low level. If you're a government operative, they don't really have the ability to block that. But at least it will stop a script kiddie who wants to distribute his malware through the App Store. So it's powerful in that sense, at least in stopping the basic abuse. But the thing is that if, with iOS, if you lose the certificate, it's not a problem, you know, if you can just wipe it. You can just essentially revoke it and create a new certificate, and you can submit every time. Now, how does that work? Because in Apple, if you try it during debug and you revoke a certificate and you create a new one and then you try to install on top of that, it won't work either. Well, the thing is that when you submit a certificate to iTunes, you have two certificates. One of them you use during debug. You use the debug certificate to install applications on your phone during development. But when you submit an app to Apple, you use a distribution certificate. Now, the moment you use a distribution certificate, you can't install it on your phone. You can only submit that app to Apple. And that app is reviewed by Apple engineers. And once they reviewed it, they sign it with their certificate. And that's the one the device checks. So when you install your own app from the store, it will be signed by Apple as well as you. And the thing is that when you want to, say, replace it with your own copy during debug, you won't be able to because the certificates will collide. So they have a similar approach to security as Google has, where they check their certificates during install. But the thing is that they take the responsibility of what's the allowed certificate. And I'm sorry, I might have made it more complicated than it is. Actually, no, it's already too complicated to begin with. It's not my fault. I'm blaming Apple completely. But generally, you have two certificates. You can use the debug version to debug. You can use the release version only to submit to the App Store. Or for test flight, which is similar to App Store submission, but I won't go there in this slide, in this session at the moment, because that's too much. Now, the next aspect of this is the provisioning. So we have two certificates. We have a debug certificate and a distribution certificate. So, but the thing is that those two aren't enough. We need two more files that represent provisioning, and they're essentially kind of the document that comes with the app that says how that app may be used. So when during development, Apple has a special restriction where they say you can't install on more than 100 phones during development. And the reason for that restriction is don't circumvent the App Store. If you can install an unlimited amount of devices, then you could theoretically just put the app on your website and that's it, and people will just go out and install it. So by limiting the install number to 100 devices, and not just that, these 100 devices, you can't just add and remove devices willy-nilly. Every device you removed is sort of ignored. It still counts to your 100, and only once a year when you renew your certificate do they allow you to wipe the slate and start in a clean situation. So the provisioning profile during debug includes that list of devices where you're allowed to install, and without your device being listed there, you can't install onto your own device. So that's really important. And the other things that it includes are all sorts of, are you using a specific API like iCloud, like Push, like things like that? All of that is itemized within that file. So you still need it even for distribution. And it includes all sorts of information that Apple needs when they install, when they test, when they deploy that application. And the provisioning is also directly tied to the certificate. So if you revoke the certificate, you need to download a new version of the provisioning with a new certificate. The other way doesn't apply. So if you make change to the provisioning, you can just download the new version and the same certificate will still work. And that's useful. One thing that I didn't mention in the slides, not sure if I want to go into it too much, but you can use the same certificate for lots of projects with iOS and also with Google if you want to. Although that's a completely different debate whether you should. But in the case of iOS, you should usually use one certificate for debug and one certificate for distribution for all your projects, and just generate provisioning for each one, because the provisioning would usually be different, and that's more convenient. Obviously, the moment you revoke or need to update the certificate, because once a year you need to update the certificate from Apple, then you need to go over all your projects and update that if all the active projects with a new certificate, a new provisioning, and it's tedious. And the last portion I want to talk about is the push certificate. And well, technically I don't really want to talk about it because I didn't mention push here, which is a big complex subject. I want to talk about it separately. But generally push allows you to send data to the device. The reason I'm talking about that is that if we're talking about certificates, there's also these, and iOS also has certificates for push. Now this is a huge, if we thought push was confusing on iOS, it just got worse. And I've seen so many people fail on this particular nuance. So we have the debug push, we have the distribution push, but we also have two push certificates. Did I say debug push? I meant debug certificate and distribution certificate. We also have two push certificates, one of them for the Sandbox and one of them for production. And the reason we have those is that when your server needs to send a push to a device, and the way this works is the server says, I want to send a message to device X that's out there. So it just connects to, usually with us, to our server, which is the Codename 1 server, but our server goes and connects to the iTunes server and tells it, notify device X that such and such happened. So that server needs to authenticate me, and for that it needs a certificate that indicates who we are, and that is also a certificate that we need. We need two of them because there's two push environments. One of them is used during debug, which is the Sandbox, and another one is used during runtime, the production, and these certificates are completely different from build, and during build we don't even know they exist. So don't confuse those two groups of certificates. They're completely different, although the push certificates are mentioned in the provisioning. So yeah, it's as complicated as that, but once we actually go through that, it's not as bad once you do that a few times, although it's error prone. So I just noticed that I mentioned Sandbox there and I'm mentioning it here, and here I'm mentioning it in a completely different context. And here I'm mentioning it as the application sandbox. So application sandbox is the way your app is sort of restricted. So when we install an application on a regular PC, or at least a 1990s PC, that application could do whatever the hell it wanted because it was running on our system, and it could change files anywhere and everywhere. So in PCs and Macs, we kind of restricted things a bit. Oh, you can't go to this directory if you're a regular user application, if you're not an admin, if you're not root, you can't access this, you can't access that. Well, apps take it to a whole different level. Apps are really, really, really restricted. They're installed to randomly generated directory names in some cases, and they can't access folders that aren't theirs, essentially. So on iOS, there's literally no real shared space or ability to normally communicate between apps or things like that. It's very restricted. So things like that we'd expect to exist when we're a desktop developer often just don't mean. And we need permissions to do all sorts of things, like access photos and cameras and things like that, which I'll discuss soon. So one common thing that people constantly ask about is, file pickers, or just go to the image folder. And these sort of things just don't physically exist on devices. One of the things that does exist is, for instance, we have the Open Image Gallery API. And you can essentially ask the system to pick an image file for you. And then it opens the native image picker gallery. You pick an image, and that image is sent back to your app. And initially it sounds really an awkward way to do it, but then you start thinking about it. What if an app just goes into your image gallery and starts uploading all of your images to someone's private cloud? And you start realizing that, oh, that's a huge privacy violation. So that's just impossible. Apps are blocked from even accessing the image area unless they have a very explicit permission to do so. And inter-app communication is very, very limited. One app can't access a folder of a different app, because then essentially if you have a banking app installed, it would be very heavily attacked by pretty much everyone trying to crack it to get into that sweet, sweet cache. So obviously there's a very strict sandbox between applications, and things like communicating between one app and another app is usually done through URLs, through intents, through other means. It's always awkward. We support some of that. So for instance, you can just use a URL to open a different application. That works in iOS and in Android, and often is reasonably portable in some cases. And you can do a lot of things with those sort of APIs. And as I mentioned, the permission system allows you to request abilities and essentially get them. So for instance, when we open a camera or contacts, the operating system asks the user, and that's the operating system that needs to ask it, not something that we're asking, whether the user wants to allow the app to do it. And that is a very transparent way to do it. Historically, Android didn't have that. It worked in by declarative permissions. So essentially, we'd write into the manifest the set of permissions an app expects, and during install you were prompted with the list of permissions the app needed, which was usually very unintuitive because you're looking at this huge list of all sorts of things that an app uses and you have no idea how that actually relates. So now apps in Android install instantly and ask you for permission in runtime, which is far more convenient. You still need to list the permissions in the manifest to support all the devices. And one of the nice things in Codename 1 is that we automatically scan your code and automatically insert permissions into place where it's needed. So this is almost seamless to you, and know that it's a huge pain in standard Android programming if something you didn't ask for the right permission or something like that. It's painful. So this works like that today. Anyway, background. I think this is the last section. Background is another thing where people expect things to work like they do on desktop, and in this particular case also expect them to work the way it works in Android. So this is one of those things that that changed a lot, and that's both OSs sort of gravitated to more common middle ground. And this is something, by the way, that I've noticed over the years, that iOS and Android started from very different locations, and both of them moved a lot toward one another and converged on almost anything. And you know, iOS fans say, oh, Android stole our ideas, and vice versa. Both stole a lot of ideas from one another extensively, and it's a good thing. They've both come a long way and improved as a result. So one of the examples here is that iOS didn't have multitasking at all when it launched. Steve Jobs literally said it will drain the battery. We don't want to do that, and technically he was right. Android had background processors and multitasking and everything, and initially it didn't seem that bad because the initial Android phone had decent battery life. But then once you started installing apps, you quickly found out that, oh, well, it doesn't. And the reason it doesn't is that often you don't really notice that an application is still running in the background. And if you kill it, you actually create a worse situation in some cases, because the service isn't necessarily dead and the relaunch later might occur, and it's kind of problematic. So iOS started by gravitating towards Android by adding background processors. And unlike Android that sort of allowed anything to run as a service in the background, so you could just write any bit of Java code and it will run in the background and all is good. In iOS, they required you to define a set of one use case out of a set of allowed use cases. So for instance, if you want to track location, geolocation, download a file, play music, or do all sorts of background tasks like that, you literally need to declare that about your application. And a guy at Apple during review time would actually look at that and say, okay, the particular app in question warrants that. So for instance, if you have a game that's completely unrelated to background location, and you say, oh wait, I want to track background location, and just don't tell anyone why, that might raise a flag during review, because they want an actual explanation of why you are tracking background location. And that's useful. Otherwise, all apps would just use that and waste battery, obviously, but also potentially violate our privacy. So there's good in that to some degree. Android 6 made a lot of improvements to battery life, and one of those improvements is that it curtailed some of the usage of these background services. So if you're using Android 6, you will notice that sometimes when you get back to your phone, it kind of takes a while to get going again. And the reason for that is exactly this. It sort of stops background processes in their track, and it has a system that's closer to the way that iOS works with specific use cases and things like that, so it can not waste as much battery when it's off. So we support a lot of these use cases, and we work in a way that's more similar to the way iOS works, which makes more sense from the portability standpoint. And well, but still, background processes are harder to get to work properly across platforms, because obviously the VM isn't fully running and all sorts of other things like that. It's complex. So if you're thinking about app functionality that relates to things running in the background, do your research, because it's a very tricky part of mobile development. So there's a lot I didn't cover. I sort of went over the basics here. I don't know if you knew the things I covered or didn't, but I hope I did give you a better sense of some of the less intuitive things that we have here. I think app development, when you come to it from the server side, from desktop, initially it seems very familiar, especially with Codename 1, which is a very familiar framework for desktop developers, and sometimes that's misleading. And I hope you are less misled by that, and you get a better sense that how different this is from desktop development. And if you didn't get by my awkward explanation of iOS certificates and signing, just how painful iOS signing is, then trust me, you'll get it when you actually try to go through it. And seriously, people, guard your certificate keys for Android, because if they're gone, they're gone. And I've heard the stories. There is no workaround. Google itself can't fix it. Commit these certificates to your versioning system and make sure you have them backed up before you submit your first application to Google Store. Otherwise, I don't want to talk about otherwise. That key shouldn't be gone ever. So keep it safe. That's the final word on that. And thank you. I hope you've enjoyed this presentation.